Hello and welcome to How to Break IoT Security. In this lecture I'm going to give you some basics about the IoT in general and IoT security. I'm going to talk about a very famous IoT malware called Mirai, about a firmware modification for a vacuum cleaner, about recent vulnerabilities called Amnesia 33, and about firmware analysis. Let's start. Okay, so what is the IoT or Internet of Things? Of course, at first we need some things like a light bulb, a body scale, a watch, a fridge or a coffee maker, and then we have to make those devices smart. So we're going to add a microchip to it, so a small computer basically. And once we've done that, we can connect those devices to the internet and thus to each other, so that they can become a bit more intelligent. If we take a look at the number of IoT devices, I have a statistic here. We can see that in 2020, the projected number of IoT devices, or as it says, the total installed base of IoT connected devices is projected to be around 10 billions. And in 2025, it's supposed to be even 21.5 billions, which is quite a lot. And with so many small computers, of course, we have a processing power that's more than any supercomputer, I guess. And what about privacy? So, as everyone knows, Santa Claus knows who's naughty and nice. But what do your IoT devices know about you? Of course, your smart light bulbs know when you're home, especially in the winter. You're not going to sit alone in the dark at home, so you're going to turn on the light, and so it knows when you're home. Your smart body scale and your smart fridge know how healthy you eat. The fridge knows what you take out of it, and the body scale knows how much that affects your weight. And your smartwatch knows about all your movements. And of course, all of those combined is pretty sensitive information, I guess, for most people. And so if there's a single cloud that collects all of these data, it would be obviously a target for some hackers, because it's valuable data for them as well. So let's take a look at the consequences when IoT security doesn't work as intended. So what I have here is a news article from Ars Technica. It's a bit older, from 2016, and what happened there was a large DDoS attack, so a distributed denial of service attack. Basically, more than 145,000 hacked cameras sent requests to the very same target. And of course, any server would be overwhelmed by that number of requests. And if we take a look at the article, it says it was 1.1 terabits per second, which is quite a lot for a DDoS attack, and not many target servers would be able to defend against that. Another news article, maybe a bit more personal consequence, is about a woman that was concerned about her children. So she installed a smart camera into their bedroom. And of course, as it had to happen, a hacker accessed it, and he used it to talk to her 8-year-old daughter. And if you read this article, of course it wasn't very nice what he's done there. Another news article that I have here is about someone who hacked their own smart coffee maker. So yeah, it's a coffee maker by a company named Smarter, but sadly their firmware wasn't really smart. So yeah, it was quite easy for the attacker, so the owner in this case, to hack his coffee machine. They just need Wi-Fi access to it, so they need to be near the device, and then they can install their own firmware and control any functionality. So it simulated a ransom attack against a coffee machine. Yeah, as I can imagine, a lot of people would pay a ransom if their coffee machine wouldn't be working in the morning. So yeah, why is this such a big problem in IoT? So basically we have some conflicting priorities that manufacturers have to care about. On the one hand, we have security. Obviously we want secure devices. Then we have usability. So users want a device that's easy to use. Price, of course, is important. Everyone wants to spend less money and energy, especially for battery-powered devices, is very important. So yeah, for example, if we want a very secure device, of course we would have to spend more money on security engineers to make the product safer, which would increase the price. And yeah, if we use better crypto in our chips, this increases energy consumption. And yeah, so there are many conflicts where you have to set priorities, and sadly in a lot of cases security is not really a concern for the manufacturers. Okay, so since we have seen that IoT devices have some specific needs, it probably doesn't surprise you that they also use specific protocols tailored to those very needs. One example would be MQTT, which is the message queuing telemetry transport. It uses a publish-subscriber architecture. So yeah, as you can see in the image here, the devices can subscribe to different events or publish events on their own. So for example, the heater on the left here would subscribe to window events, and once the window opens, it can send such an event itself, and the broker in the middle would take care of where to route that message to, so only the subscribers should receive it. And this is a very simple way to connect many IoT devices without knowing upfront which devices you're going to have in the end. It's easy to implement, at least in contrast to some other protocols. It also works if the network is unreliable, which is a big plus. This means that the broker, which is always in the middle of a message, can store a message once it's received and keep it until the receiver is back online. So if a connection breaks, it's not too bad, because the message can be delivered later. It's based on TCP/IP, so yeah, you can use Wi-Fi or Ethernet or whatever. You can do some quality of service settings in a message. It should be delivered at least once or exactly once, stuff like that. And it has support for TLS, which means that messages can be encrypted, transport encrypted, that is. So the next protocol would be CoAP, which is the Constraint Application Protocol. The architecture is a bit simpler here. so devices connect to each other directly. Yeah, it's a lot like HTTP, and that's on purpose because yeah, it's kind of a binary HTTP, so it uses the well-known request types which are used in the HTTP standard, like GET or POST, but it doesn't send it in a text format, but in a binary format, which saves some bytes. And yeah, the standard is also a bit shorter, so it's easy to implement on devices which have limited resources. The next protocol would be LoRaWAN, which is the Long Range Wide Area Network Protocol. And it's a radio protocol, but yeah, as the name suggests, it can send messages over very long ranges. So yeah, it is said to have in line of sight communication about 10 kilometers, which is the maximum, but you can expect something between 0 and 10 kilometers. In cities, of course, it would be less, but it is very well suited for long-range communication and also for saving battery. And yeah, so it uses a lot less energy than Wi-Fi, for example. It has more range, but on the downside, you have less bandwidth available, and you can only send messages every so often, depending on how many other devices there are on the network. So it could be possible that you have latencies about multiple minutes between messages, which of course for an alarm system, for example, wouldn't really be great if you wait half an hour to receive your alarm message. Another downside, or basically it's always the case with radio protocols, you need base stations. And luckily the Things network provides such base stations and connectivity for free, so anyone can use it. And yeah, as I said, the bandwidth is rather low, less than 50 kilobits per second. Another protocol would be ZigBee. So yeah, this is another radio protocol, but it will typically not be used in long-range communication, but more like in your own house. So if you have, a common application would be light bulbs and light switches. And a neat feature of ZigBee is that if the sender and receiver can't communicate directly, because there's a concrete wall between them or something like that, they can use some other devices, some intermediates, to route the message through the network to the receiver. So for example, if you have some ZigBee light bulbs in your house, those can act as a router and make sure that every device gets their messages delivered. It's an open standard. It's widely distributed through Philips Hue. You probably have heard about it. It's a mesh network, as I said, and it specifies not only how data is transferred, but also some interfaces. So basically it says a light bulb has to accept this functions. It has to switch on and off, maybe control the brightness, which is nice because it means that devices from different vendors can communicate with each other. That should be enough for IoT basics. Let's talk about IoT security, or rather IoT insecurity in this case. I'm talking about Mirai, which is an IoT malware. It wouldn't attack like your home computer or your smartphone or stuff like that. It was specifically made for IoT devices. So it used a different processor architecture and some IoT-specific attack vectors. and yeah, it was pretty widespread in 2016. At times more than 600,000 IoT devices were part of the botnet, quite a lot. And yeah, I've talked about it earlier. It was the one that caused the 1.1 terabits per second DDoS attack against OVH. So yeah, it was quite a big news back then. Yeah, after it caused some damage, first the author decided to release the source code, yeah, to make it harder to track them and to enable other people to use the malware. So yeah, they even provided some helpful instructions on how to configure the bot and the control server, and this enabled other people to build their own versions of Mirai, which use different attack vectors, but more on that later. The original Mirai used a pretty basic attack vector. Yeah, it's a brute force attack against telnet servers. So it contained a word list of only 63 entries. Yeah, you can see the first of them here on the screen. Root and admin, not really secure passwords, but it managed to infect hundreds of thousands of devices, which, yeah, of course, isn't really a good sign for IoT security in general. There were some Mirai variants that were more sophisticated. So one of them attacked routers. So yeah, DSL routers actually, which you would have in your home to provide internet connectivity. Yeah, it attacked speedport devices provided by Deutsche Telekom for their customers, and it used a vulnerability in their implementation of TR69, which is basically a remote control protocol that allows the ISP to change some settings in your router or install an update, stuff like that. And yeah, what it did here, the malware sent a message to set a new time server, but it didn't actually supply a time server, but a bash command. And yeah, this was enough so that the router would execute the command and download the malware and execute it. Yeah, this caused a lot of customers to lose their internet connectivity, and it was also a news story back then. A different one was also targeting routers, but routers made by Netcore or Netis. And yeah, what's interesting here is that the vendor actually provided a backdoor into their own product. So yeah, they used security by obscurity in this case. So someone had to send a very special UDP packet to a port, and yeah, that backdoor could be used to execute arbitrary commands and yeah, thus infect the device. Another variant yeah, used also a vulnerability in a router. Yeah, you can see the details in here. It was targeting Huawei routers, so something else this time. But yeah, you can see that malware used some yeah, very general attack vectors that would work against all different types of IoT devices, and also some specific attack vectors that were yeah, to be found in very widespread devices. Okay, so our next topic is related to this device here. It's a smart vacuum cleaner called Mi Robot. Yeah, you can see all the sensors it has in this picture. For example, it has a LiDAR, a wall sensor, a dustbin sensor, a collision sensor, an ultrasonic radar sensor, an electronic compass, a cliff sensor, a gyroscope and an accelerometer, a drop sensor, a speed meter, and a fan speed sensor. So yeah, it's actually pretty advanced. It does some intelligent planning beforehand. So it maps out your rooms with the LiDAR and then decides what the best route would be to clean all the ground. There are also some other vacuum cleaners that would just bump into all the walls until they think they have covered enough ground, but this is one of the better ones. And it's also rather cheap actually. You can get it for 150 euros now if you find the right deal. So yeah, of course, a lot of people bought it. However, there are some problems with it. Usually a user would use their smartphone to control it. So yeah, to see if some filters have to be changed or yeah, where it went on its trip, or to set some timers, stuff like that, they would use a smartphone app. But it also had a connection to a Chinese cloud, both of which were encrypted, so you couldn't really see what data was transmitted there. And yeah, some privacy activists didn't like it and chose to investigate what it transmits to that cloud. So they tried reading the firmware from the vacuum cleaner. Yeah, they actually used some aluminum foil to access it, to get the firmware. If you want to know more about it, there's a talk which you can find. I'll link it up here somewhere. It's really great. You should watch it. It's very interesting, and yeah, if you want to know more about this topic, you should watch it. But what they found when they looked into the firmware was how the update process of the vacuum cleaner works. So the first step would be that the vendor, the manufacturer, Xiaomi, sends an update message to the vacuum, which includes a URL where the firmware image can be downloaded from, and an MD5 hash. So the vacuum cleaner can verify that nothing got damaged while downloading. Then the second step, of course, would be to download the update from that URL. The next step then is to check it against the MD5 sum it received earlier. Then it decrypts the firmware image using a symmetric key and writes it into the internal flash memory. Yeah, you can take a look at this and decide for yourself, do you think it is secure, this procedure? Yeah, take a deeper look at it, and there are some problems actually. So first of all, maybe the most obvious one is that MD5 is known to be broken, so it's possible to find, rather easily, I would say, with only a few weeks or months of processing power, to find some collisions, which means a different plaintext which would result in the same hash. But it's not a big concern here actually. The second is that the software accepts arbitrary update URLs, so it doesn't have to be a firmware image hosted by Xiaomi. It can be on any web server. Of course, a problem would be that the symmetric key, which is on the vacuum cleaner to decrypt the image, can also be used to encrypt an image. So yeah, this doesn't really add any security. As soon as you have one of those devices, you can encrypt your own firmware, just like Xiaomi would be able to. And yeah, what did they do to upload their own firmware onto the robot? First of all, of course, they used the key from the robot to encrypt the firmware. They uploaded it to their own web server. Any web server would do. Calculate the MD5 hash because it's needed in the message, and then send the update message through the app interface. As I said earlier, it can be controlled either through the app or from the cloud, and the robot accepts either for update messages, so you can just install your own firmware image if you have access to it through the app. Then you just have to wait a few more minutes for the installation to complete, and you can execute whatever code you want on it. If they included SSH in their custom firmware, they would find out that the robot is actually running a stock version of Ubuntu, which is a common Linux-based operating system. And they would now have full root access to the robot. They could install anything on it, like an internet radio or a different version of the cleaning system. And they, of course, could get rid of the Chinese cloud. There are some alternative implementations like Valetudo, which installs an interface like this, so you can control it from your own network. Our next topic is Amnesia 33, which is a collection of 33 different vulnerabilities found across 4 TCP/IP stacks, which are listed here. What kind of vulnerabilities are those? What I have here is a screenshot from the US CERT advisory on the topic. Under executive summary, it draws attention to the fact that it's exploitable remotely and that it needs a low skill level to exploit. Under risk evaluation, they say that successful exploitation of these vulnerabilities could allow attackers to corrupt memory, put devices into infinite loops, access unauthorized data, and/or poison DNS cache. Of course, you wouldn't want anyone else to be able to do that to your devices. And what's making this even worse is that the vulnerabilities are inside the TCP/IP stack. If you receive an IP packet, or your device rather, at first it lands in your hardware, for example in your Wi-Fi adapter or your network card. Then it goes on to the TCP/IP stack, where the firewall is, where routing is done, and then onto the application, so for example a web server. And what this means is that even if you have no applications running whatsoever on your device, or if you have very strict firewall rules that reject any incoming packets, you are still vulnerable to these attacks because they target the TCP/IP stack directly. So this makes it even worse. So you may ask how they found 33 vulnerabilities, because of course it's not like you read the source code for 5 minutes and then you found the vulnerabilities. It's actually a lot harder. And they used a quite clever tool here, which is libfuzzer from the LLVM compiler. A fuzzer is a special program basically that's running your target software inside it. And then you can use it to to feed data into the target software. So you define a function, for example, in this case, a function that receives some network input, and you tell the fuzzer to feed random data into it, and then the fuzzer analyzes the software, sees which code paths were used and which were not, and it tries to change the input data so that different code paths are used. And yeah, it basically tries to find some unexpected behavior in programs, for example, crashing or sending back some memory which is not supposed to be sent back. Another tool that they used is this Yearn open source code querying software. And of course, they also manually looked at the source code. Since it's open source, it's a bit easier to find out what's happening behind the scenes. If it were a closed source product, that would be called a black box test. It would make things a bit harder. One example, one vulnerability that they found, I have the source code here, which is in the Pico TCP, I think it's called, stack. What you can see here is a function that gets called when an ICMP package is received. This is used by the ping command, for example. The echo variable is the input, and as you can see, they read a header value from the input packet, which contains the transport length, so the package size, and then they use that to copy data from the device memory. So if you change the packet length to 0, for example, this would be a negative number, and since it gets casted to an unsigned integer, it becomes a very large positive number. So you end up sending back a lot of data that shouldn't be supposed to be sent back. Another way to find vulnerabilities in IoT devices would be firmware analysis. Like the guys did with the vacuum cleaner, to find out how to break the update process. You could basically do that with any device. It has some advantages to working with the device directly. First, of course, you don't need the actual device, so you don't need to buy an expensive vacuum cleaner or fridge or body scale or whatever. You can just use the firmware image itself, which you can download on the internet, if you want to find vulnerabilities inside the firmware image. Secondly, if you want to find some hidden functionality, so like a backdoor, for example, as I've talked about earlier with the router, which had a backdoor, you probably wouldn't find it by randomly sending data to it. You have to analyze the software that's running on it to find out how to exploit it. And of course, it can be easily automated, which is always nice. So some examples of what you can do by firmware analysis. Firstly, of course, you can identify the software that's part of the firmware image. This would usually include like a web server or an MQTT client, stuff like that, and you can find vulnerabilities for the specific versions of that software. You could try to find some common weaknesses in the implementation, or usernames, passwords which can be used to log into the device, some key files that may be left, and those are just examples. There are many more things that could be done. Some tools that would enable this include FACT, which stands for Firmware Analysis and Comparison Toolkit, and Radar 2. We actually have the first one running here, so I can just show you how it works. So it's a web-based system, which means you can just run it inside your browser. So as you can see on the front page, it shows some statistics about the firmware samples that have been uploaded. And more interestingly, if we go to the upload page, you can just choose the firmware file which you have downloaded earlier and upload a new image. And you can select which kind of analysis should be done on the firmware sample. For example, you could use binwalk to do some entropy analysis. You can find out the CPU architecture, which crypto algorithms are used, if there is any crypto materials like private keys left on the device. You could check for CVE vulnerabilities, common weaknesses enumeration, known vulnerabilities like Heartbleed, and usernames and passwords, like I've explained earlier. Let's take a look at one sample. Let's use this one here. It's an IP camera. One of the groups is actually using it for penetration testing, so I hope I don't show too much information here. Let's just look at the software components. As you can see, it identified quite a lot of components inside, like BusyBox. BusyBox is a toolkit for embedded devices, which includes a shell or some basic programs like tar or ls, for example. And let's just see if some vulnerabilities were found. BusyBox is always a good candidate for that. As you can see, there's even some critical vulnerabilities, the same in curl and the Linux kernel, and OpenSSL. So this is nice for a penetration tester, of course, to see something like that. Let's see what we can find for BusyBox with this version. This is the National Vulnerability Database, and we can just search for the version that we found inside the image, BusyBox 1.24.1, and list the known vulnerabilities. Okay, so as we can see, we have 9 vulnerabilities, and some of them are critical, like this one here, a vulnerability in wget, which is a program to download files from the internet. Or here's another one in the UDHCPC client. Of course, both of those are exposed to the network, so it might be possible to actually exploit the vulnerabilities. Okay, to conclude this lecture, we have learned that the IoT poses some unique challenges for security. We have seen that IoT security will get more relevant in the future with all the IoT devices which are projected to be added to the internet. And there are many different ways to find new vulnerabilities. Okay, that's all for this lecture. Thank you very much for your attention, and bye-bye.